Well, I hope you find this video helpful. I'm going to use this to kind of help you fill in your notes while I'm gone. So I hope this helps out. And I'm going to tell you right now, it's kind of a difficult thing to find a quiet place in my house. So if my dogs start barking like fools, I'm going to just kind of keep on going. So please bear with me. But this section is really talking about subatomic particles and applying what you know about them to kind of describe how an atom all the characteristics of an atom. Okay, so of course, first of all, we should define the atom, and as you probably already know, it is the smallest particle of an element that retains the properties of that element, and it's really our building blocks, aren't they? And we first got to take a look at what an atom would actually look like using a microscope in the late to mid 1980s. Gerd Benning and Heinrich Rohrer actually won the Nobel Prize for this. And while this isn't going to be on your test, I did want you to at least take a look at some of the images that they can get from an STM, a scanning tunneling microscope. And they're actually pretty cool if you look at some of the pictures. This was probably, I'm going to guess it's an iron atom. It might be a different one, but most of these are done on a flat, atomically flat piece of copper. And this picture down here, you can kind of see the rings, the energy levels around it. So that's one picture, but you can tell that people have gotten pretty creative looking at these things. Artists have gotten a hold of this and kind of played around with it a little bit. This one is actually fairly famous in the STM world, and this one is called a quantum corral. And these are all iron atoms with these red peaks on here. And again, this is on a copper plate here. Okay. Again, just wanted you to kind of see what these things look like because it's pretty big deal to be able to take a look at these things in real life for the first time. And now I want to start talking about some of the fundamental subatomic particles. And we always start with the electron. The electron was found using what's called a cathode ray tube. And this cathode ray tube, I'll switch over here just for a second, so we've got this glass tube, okay, and it normally has something down here at the bottom that actually is hooked to a vacuum to pull all the air out of there. And they hook it up to a battery, run an electrical current through it. And in this cathode ray tube, what they were finding is when they turn on the battery, hook this up, they get this ray, this green ray that was going across here. And no matter what they did, no matter if they changed the metals of these cathodes and this anode, it didn't matter. They were still getting this same ray. So this cathode ray tube is producing this cathode ray, and scientists started playing around with it, trying to see what they could figure out what this ray was. But one thing they did know is this ray was coming from all types of metals. You know, when they were changing those anodes and cathodes, they were still getting this same stream. But when they were playing around with it, they did so with an electromagnet, and they found out that these things were negatively charged. So I'm going to attempt to play a video within a video here and see how this goes. But what I want you to see, so this is our cathode ray in a cathode ray tube. And what you're going to see is somebody up here at the top is putting an electromagnet down here on this cathode ray. And the first one, as you see, is going to be a positive electromagnet. And we can tell because it's actually attracted to that, and it bends it up. But if you look, now they're doing a negative one, and they can push it all the way down and actually move it, like do considerable movement with this ray, with this electromagnet. Okay, so that's kind of what it looks like in real life, just to kind of give you an idea. And here we go. So what they have now, or what we've found from this cathode ray tube, is the electron that we now know as the electron, and it's negatively charged. We also know that it is in all forms of matter, again, because they changed out those metals, and we're still getting this same cathode ray out of it. Okay, so a gentleman called Thomson actually received the Nobel Prize for this back in 1906 for identifying the very first subatomic particle. Again, I'm not going to be testing you on names and dates. That's not really how I function. That's not really my priority. But the things I want to make sure that you do know is, one, cathode rays were a stream of charged particles. Of course, we found this by using electromagnets. The particles carried a negative charge, okay? And changing the metal that made up the electrodes on either end of that cathode ray tube did not change the ray itself. Therefore, they concluded that all matter must have these particles in it. And then the next comes Millikan's oil drop experiment. And this happened shortly after the electron was discovered. So if you look in 1910, somewhere around there, Robert Millikan started messing around with the oil drop apparatus. And what he was really trying to do is figure out the charge of an electron. So he's spraying this oil into the canister here, and he was getting the oil droplets to kind of hover between these two charged plates. And because he could measure the charge on the plates, he was actually able to measure the charge on the electron. And with a little bit of calculations here, we now know that the charges are actually in an electron are equal to 1.6 times 10 to the negative 19th coulombs. So that's what he kind of got out of that. Now we just call it to the negative first. So of course you don't have to memorize this coulombs part, but when we compare the charge to the electron, it's comparable to the charge of that of the proton. So we kind of simplify that a little bit and just call that to the negative first. But to kind of put it into perspective, lightning probably ranges in and around 25 coulombs, I believe. So hopefully that kind of gives you an idea. So with the electron's charge, he could also get the mass of the electron. So that was yet another calculation. Again, nothing you need to memorize, but it is 9.1 times 10 to the negative 28 grams, just to put things into perspective. And it is 1/1840th of the mass of the hydrogen atom. So collectively, what we kind of do with the electron is it has a -1 charge, but to put things into perspective, we normally call it zero mass. Is the electron really massless? No, it isn't. But relative to other subatomic particles, fundamental subatomic particles, it is zero. So that's what we use. All right, so now that we know that electrons exist, okay, Thomson starts working around with this idea. And the thing is we know that matter is neutral. And because we know that there is a negative charge inside the atom, then they know that there must also be some kind of positive charge to counteract that. Because again, matter is not all negatively charged, so there has to be something there. So the first idea is what we call the plum pudding model. We kind of have this mass of positive charge, okay, that's kind of evenly distributed with these little negative charged electrons in it, almost like a chocolate chip cookie, but try and think of it as like three-dimensional, okay? And so then, and this was Thomson's idea, the same guy that discovered the electron. And then somebody in 1911, Ernest Rutherford, was trying to take this idea of the plum pudding model and tried to test it to see if that was actually what was going on. So what they expected to happen, what they did is they were shooting alpha particles through this atom, and what they expected to happen is to have all of these alpha particles go directly through the plum pudding model. Okay, they were all going to just zoom right through here, right through that positive mass. But actually what happened is something quite different. So the setup kind of looks something like this. They have a lead box, of course, to protect them from the alpha particles, and they have an alpha particle source inside the box that's emitting these alpha particles, and they're shooting it through this gold foil here. So they're thinking that the atoms, the gold atoms, are going to allow these alpha particles to go straight through, which some of them do. But what they didn't expect were these reflections of the alpha particles at these sometimes extreme angles. And so what they conclude is obviously this alpha particle is hitting something. It's bouncing off of something. So then our model starts to change a little bit because we have this repulsive, dense center that the alpha particles are hitting and bouncing and reflecting off of. So something definitely different than what they were expecting in the plum pudding model. So what we end up with, what Rutherford comes up with, is this dense this dense part in the center of the atom is now called the nucleus. Okay, and probably the other thing that is a really, really important conclusion that people miss here is really the atom is mostly empty space, because if you remember, most of those alpha particles did go straight through. So the atom is mostly made of empty space. But almost all of the atom's positive charge is made, and mass are all contained in this dense region called the nucleus. And then the electrons are held within the atom by the attraction to the positively charged nucleus. So that's where we are now. And to put things into perspective, I want you to know that the nucleus is extremely tiny compared to the overall size of the atom with the electron cloud. In fact, if the OSU stadium, the horseshoe, were an atom, the nucleus would be about a golf ball on the 50-yard line. So we're talking vast differences in size here. Very, very dense center. So after Rutherford has discovered the nucleus, we now have what most people think of when they think of an atom is this drawing here. And this was made by a man called Niels Bohr. So this was his model. And he's thinking, not here's the nucleus, relatively out of proportion, but you get the idea. We have this dense nucleus. And so the thought is now that these electrons are orbiting almost like in planetary motion around the nucleus. And this model stayed around for a really, really long time. It was definitely what most people thought of when it came to the atom. However, I think it's very important to state that this is not accurate. Okay, this is what most people think of, but it is far from an accurate model of what we know today about the atom. So now that the nucleus exists, Rutherford refines the model to include this positively charged particle in the nucleus, and this particle is now called protons, the protons. And James Chadwick, who comes along quite a bit later, if you look, it's 1935, when he officially discovers the neutron. But here's the thing. There was a long period of time, because it took him a really long time to actually prove that the neutron existed, but they knew something else was in there. They knew about the protons, they knew about the mass of the protons, but they also knew about the mass of the atom itself. And there was definitely a difference between the mass of the atom and the mass of the protons. So they knew something else was in there. But the fact that they were neutral particles kind of made things a little more difficult. And I mean, it's an interesting story about how they finally were able to prove that they existed, but it won't be anything that we cover here. All right, so we now know that the nucleus, of course, is made of the three fundamental, sorry, not just the nucleus, all atoms are made of three fundamental subatomic particles. The electrons are in the electron cloud around the nucleus, and in general, atoms are spherically shaped. Now, the chemical behavior of all atoms can only be explained by taking into the consideration of their electrons. And in fact, our next unit will be only about electrons, just so we can really talk about the chemical behavior of the atoms and get a better understanding for it. But until then, I think it's important to know that all chemical properties are based on the electrons, and the atom itself is mostly empty space, and the electrons travel around the nucleus. However, they are not in orbit, and we'll go into that a little bit later. Okay, so to sum things up here, we have the three fundamental particles here: the electron, the proton, the neutron. The symbols, we have the small e with the negative sign, the smaller p, oftentimes you will even see a positive sign there, and then the small n. Their relative charge compared to each other, -1, +1, and 0. In terms of relative mass, when I ask you, if you want to put 1 over 1840, you can, but relative mass is 0 for the electron, and I'm okay with that. And while this is extra information over here, I'm not really expecting you to memorize those, okay? But it does kind of put things, again, into perspective. All right, and of course there are other particles in the atom, not just our three fundamentals, but there are other elementary particles as well. And we have fermions, which include quarks, leptons, antiquarks, antileptons, and all of these are considered matter particles. And then there are bosons, gauge bosons, Higgs boson, which is fairly new, and these are all considered force particles. So each of these fermions and the bosons give characteristics to the atom itself. Okay, so these fermions give things matter, are considered mass, and then our bosons give us force. Now Higgs, though, Higgs is, like I said, kind of special, and I'm going to have you take a look at a video that was just on Higgs and its discovery. So just a little more detail with quarks here. Quarks are elementary particles that help kind of make up other subatomic particles, and there are 6 types. And yes, I know this sounds strange, but they are known as flavors. Up, down, strange, charm, bottom, and top. Those are the flavors of quarks. Up and down quarks make most common and and the most stable out of all the flavors. Up-down quarks are produced from other heavier quarks through different particle decay. So they're like I said, they're the most common because the others tend to break down into that. Okay, things you should probably know: a proton consists of 2 up quarks and a down quark. And a neutron, slightly different, but I bring this up because it's going to come up in nuclear decay. A neutron is 1 up and 2 down quarks. So if you look, they're really not that different, and this explains a lot about why they have very similar masses and yet just a different charge. So good reasoning for that. So again, a Higgs boson is something kind of special, and what I'm going to do, I'm not going to play another video in here. I think this one's gone on long enough. So hopefully this helped you with your notes, but what I would like for you to finish up, I'm going to it's already posted. This video right here about the Higgs boson is already posted on It's Learning, and I would appreciate it if you would take the time to watch that as well. So I hope this has been helpful. Again, if you have any questions, please feel free to email me, and I will get back to you as soon as I can. Okay, take care.